Yeah, where we left off is we said, hey, if this train is moving to the right, that we would end up seeing that from a person on an outside perspective would see that it is moving to the right, the center right here. But if we're on the train, we would see that it is heading towards each other, and so therefore it would be 0. And so we ended up saying, where is the center of mass going? And so that's where we left off. What's weird, what's kind of funny is we're not even talking about center of mass today. We are starting combo problems today. Combo problems. And so we've got this new crazy roller coaster. It's designed around a large mass of silly putty, TM. Is launched at the back of the roller coaster to propel it forwards as shown. Suppose the mass of the silly putty, TM, is 250 kilograms and the mass of the coaster is 1,500 kilograms. The silly putty is fired at a speed of 60 meters per second and sticks to the coaster. With what speed will the silly putty and the coaster travel immediately after the collision? All right, collisions. Is that work, energy, mass, force, momentum? What kind of idea is that? Momentum. All right. So when we have a collision, we're going to conserve momentum. Conservation of P is that the P initial equals the P final. And I'm going to talk about this at point 0 versus moment number 1. What about the energy? Is this elastic or inelastic? Elastic or inelastic if it sticks together? Inelastic. Okay. So if it sticks together, it's inelastic. And so we have at the same moments that it does not equal, right? Do you remember that? We're going to lose some energy where it's going to not be in the problem anymore. It's not destroyed, but we just can't keep track of it as easily. Okay? But then we have a whole roller coaster, and we've seen roller coaster problems before, even ones with the loop-de-loop. What were we worried about when we were tracking the energy as it goes through a roller coaster? The final and initial what? Kinetic and potential energies, right? Energies. So the energy at moment 1 will equal the energy at moment final anywhere along this roller coaster track. I could have put 2 there. But what are we going to say about the momentum? Do we track momentum as it goes up and down the roller coaster? Does the momentum change as it goes up and down a roller coaster? Yes, it changes. Can we track it easily? Not really. It'd be like, oh, hey, look, there's a momentum shift because we went up a hill. We slowed down. Less momentum. But where did it go? The potential energy. And so we're not going to track the momentum at this moment. Okay? So 1 and final. Doesn't matter as much. All right. So a new roller coaster is designed. We read that. What's going on? We have a silly putty hitting a coaster. The silly putty was fired at a speed. What kind of problem are we setting up for the silly putty and the coaster getting hit with a collision? We have a collision. So the momentum equals the momentum. Initial and final, right? Before and after. And you said inelastic, so I'm going to write M1V1 plus M2V2. Or A's and B's, doesn't matter. If I'm already using too many 1s and 2s, you could use A's and B's. Equals. They're stuck together. How do you do that? Add them. They're stuck together. M1 plus M2. Add them. And they're traveling together, so they're going to have the same velocity. So this is why we factor. I think we just plug it in at this point, yeah? 250 times 60 meters per second plus 1,500 times 0 equals 250 plus 1500 times velocity final. That cancels out. We have VF equals 250 times 60. That's 15,000. Divided by 1750. What's our VF? 8 meters per second. Good. 8.57 meters per second. In the space below, we're going to sketch a graph that represents the momentum of the silly putty. First off, it says sketch. I don't have to be perfect. I don't have to graph it. I don't have to draw it like when the test said draw a graph. You had to have the actual exact values. But we might as well figure out what those values are. Do we have the what is it? The momentum of the silly putty before? What is that? 250 times 60, right? Momentum initial. Then the momentum final is going to be same mass, 250 times. Do we have a new speed? 8.57. It only asked us for the momentum of the silly putty, not the whole system. So make sure you're answering the question. The momentum of the system stays the same. The momentum of the system is conserved, but the momentum transfers from the silly putty into the coaster. That's what they're really asking. So I think that's 15,000. And the second one is 2,000 what? $2,000. Good. 2,142 point something. I said that this one should be about 7 times smaller than that one. And because this is a sketch, I'm not going to even worry about labeling my axes. I just need to know that this is the initial. And this is the final. So I could say that it's the time immediately before and immediately after. I should probably say before and after to answer my question in terms of the wording of the question. But I think this is interpretable, especially since it says sketch. What fraction of kinetic energy was lost during the collision? Wait, kinetic energy? It's not asking us about momentum anymore. So what fraction of kinetic energy is lost? How do we find out how much kinetic energy was lost, first off? What's the kinetic? Yeah, you're answering the question I'm asking. 1/2 mv squared. And it's going to be the lost energy, so minus 1/2 mv final squared. So we can figure out the energy that goes away, that we can't find anymore. 1/2. What's moving at the beginning? What's providing the kinetic energy at the beginning? The silly putty. So 1/2 250 times 60 squared minus 1/2. And the kinetic energy is found in both items at the end, right? So 1750. And the speed is 8.57 squared. That's my numerator. What do you mean, Mr. Kwan? It says what fraction of kinetic energy, and so it's going to actually be a proportion. This is the amount of kinetic energy lost. 1/2 250 times. Wait, what is that anyway? It's like 450,000 minus. That's the first half minus the second half is like 60. I'm checking 64. 264 joules of energy. That's the amount lost, but it says what fraction is lost, so it's the whole. 450. Yep. 450,000 is the whole starting energy. And so that's the amount of proportion of energy. I ended up getting 0.86, or 86% of the energy is lost. 86% of the energy is lost. So not very efficient at all. Silly putty roller coaster doesn't make much sense. Also, where did it go? So heat lost. Heat is the rearrangement of molecules and atoms. So I would say that this probably went into the deformation and splat sound of the, hopefully the cart doesn't change shape. So the silly putty. That's the official answer. Is it heat? Kind of, sort of. This would be a little bit more recognizable than just heat itself. A little bit more organized than heat itself. Will the velocity of the silly putty's coaster's center of mass remain constant as it travels up and down on the track? Look at the track. Is the speed going to stay the same? No. What's probably going to affect us? Our speed will be affected by gravity. If I pick the wrong one ever, just blame it on me being a lowly physics teacher. I'm not an English teacher. Silly putty coaster reaches the top of the hill. Height h with the speed of 5. Calculate the unknown height h. What kind of problem is this? We're going to have some sort of potential energy. So we're in what topic at all? We're not in momentum, we're in energy. So the conservation of energy of after the collision, but as it rides down the coaster, is going to be we're going to start with some sort of speed. You're right. So 1/2 mv squared. And we're going to turn that speed into mgh. Is that it? I think we still have a speed. So plus 1/2 mv squared. Alrighty. What's the mass of the item that we're talking about? Is it just the coaster? Or is the silly putty still attached to it? Okay. 60 squared. Is that the starting energy? 60? It's the whole thing. Yeah. It's 8.57. Equals 1/2. It's the whole thing in 1750. What's the new speed at by the end? 5. It tells us in this question. 5 squared. Plus mg8. Wait, we know m. We know g. 1750 times 9.8. So we can solve for h. (8.57) squared minus 5 squared all over 2 times 9.8. I got 2.47 meters because the height. Double, triple check all your units. Make sure they're all in meters. Make sure they're all in seconds. Make sure it's all in joules of energy. Make sure it's all in regular SI units, kilograms, things like that. And then we should be good to go. Let's talk about the lab activity. The lab activity is posted online. It's very similar to this problem. The lab activity, we're talking about the transfer of energy. I'll show you a video after I get done with this recording.